Hi, George Diamond here again. Now today we're going to look at another application involving the fundamental theorem of calculus. Let me put my soccer ball down over here. We'll get started with our video. Now, so we're still, in our textbook, we're still in section 4.4. This is the fundamental theorem of calculus, the first part of the fundamental theorem of calculus, and part 2. Now, what we're going to look at today is motion of a particle. Now, motion of a particle is simply another way of writing the net change theorem. Now, we looked at the net change theorem in our last video, so we did several examples involving net change. But today we're going to apply the net change theorem to motion of a particle along a line. Now, so as it turns out with the net change theorem, when we integrate over a time interval from A to B, the velocity function. Okay, integrating the velocity function gives us the position at B, okay, minus the position at A, which is simply the displacement of the particle. Displacement is simply the net change in the position of the particle relative to its starting point. All right, so once again, when you integrate a velocity function with respect to time, from time 1 to time 2 over a particular time interval, okay, when you integrate the velocity function, this gives you the displacement of the particle. So the position at B minus the position at A, which is simply its displacement relative to its initial starting point. Now, when you integrate from over a particular time interval, the absolute value of the velocity function, all right? Okay, this will give us the total distance traveled of the particle. All right, so the particle may travel to the left and to the right, and the final position of the particle, it may not be very far from where it actually started off. So a particle may change direction, a couple of times over a particular time interval. So the displacement may not be very, very big. I mean, it may be very close to where it actually started off at. But if it changes direction a couple times, it may go to the left, it may travel back to the right, and then stop. Well, it may be pretty close to where it started, but the total distance traveled of that particle. The particle may have went to the right, and it may have gone back to the left, and back to the right, a certain distance. So the total distance traveled, it may have actually traveled a pretty good distance, but it's not very far from where it actually started, so the displacement may be very small. But the total distance traveled, it may have actually traveled a pretty, fairly long way. So to calculate the total distance traveled, you have to take the absolute value of the velocity function. Okay, that means also you have to determine, okay, does the particle change direction? Now, when a particle changes direction, the velocity is 0. All right, so when the velocity is 0, typically, usually, not always, but usually the particle is going to be changing direction. So that's one of the things when we're determining the total distance traveled of a particle, we have to determine, does the particle change direction over that time interval? Now, we're going to look at today, we'll look at, I think, 3 problems where we're going to determine the displacement and the total distance traveled using a couple different velocity functions. So some particles traveling along a line. I think we'll do 3 problems. We're going to do a couple of, we'll do a linear function, a quadratic function, and we'll do a trig function too. So let me get this erased and we'll get started with our first problem. All right. So once again, as we look at these problems, I'm assuming that you already know how to evaluate a definite integral, right? So you'll have to be able to use those skills to evaluate a definite integral, because this is what we're looking at here. And so this is an application of the fundamental theorem of calculus, so you have to be able to identify a definite integral. So let me pull up our first problem here. Now, problem number 1. Okay, so let's start with a fairly easy problem. This is just a little linear function looks like, so take a look at it. It says the velocity of a particle moving along a horizontal line is given by the velocity function v sub t equals 4t minus 8 feet per second. So time is in feet, okay, distance will be in second, or time is in distance will be in feet, so the unit will be in feet per second. Find the displacement and the total distance traveled over the interval from 0 to 3. So to get us started, now let's begin. Let's see if we can get let's determine that when we get the displacement and the total distance traveled. So let's get the displacement first. nt, so the displacement Okay, let's do the displacement first. Now to get our displacement, okay, let's set up our interval. Now our velocity function is 4t minus 8 over the interval from 0 to 3, so that we're simply integrating from 0 to 3, 4t minus 8. Okay, dt. So just integrating the velocity function will tell us our displacement. You don't have to determine any whether the particle changes direction or anything like that. We're simply looking for the position of the particle relative to its starting point. So the net change in position. Okay, that's what we're looking at here. So to start off, let's get our antiderivative. Now the antiderivative of 4t will be 4 times t squared over 2, okay, minus 8t from 0 to 3. Now simplifying this a little bit will give us, 2t squared minus 8t from 0 to 3. Now, in just a moment now, I'm going to have to take this down. So if you need to copy this down, make sure you go ahead and copy this problem down. So to give me a little bit of room, I have to take it down in just a minute. All right, now to evaluate our definite integral, we'll substitute the upper bound minus the lower bound. All right, so substituting 3 in for t first. Okay, this will give us 2 times 3 squared minus 8 times 3 minus the upper bound. This will give us 2 times 0 squared minus 8 times 0. Okay, now this is all 0. All right, so this is all 0. So as we evaluate this now, this will be, now it'll be 18 minus 24, which is negative 6. All right, so our displacement will be negative 6. Now negative 6 would indicate a displacement of negative 6 feet to the left. All right, so the particle is going to be 6 feet to the left of where it started. If it started at 0, all right, so 6 feet to the left of where it started. Okay, so this will be our displacement. Now next, let's see if we can determine the total distance. Erase this. So let's see if we can determine the total distance traveled of the particle. All right, so the displacement was negative 6. And next, let's see if we can determine the total distance traveled. So the total distance. All right. Now, first thing we got to do, we got to decide, we have to determine whether or not the particle changed direction or not. All right, so is there a direction change? And let me see if I'm going to go ahead and take this down. All right, so give me a little bit extra room here. Okay, let's see if we have a direction change. So what is our direction change? All right, here we go. Is there a change in direction of the particle now? If there's a direction change, remember that's when the velocity is equal to 0. So our velocity function is 4t minus 8. So minus 8 equals 0, that gives us 4t. So 4t equals 8. Or t equals 2. So the particle is going to change direction. Now, notice that 2 is within our interval now. We're looking at the interval from 0 to 3. So the direction change is within our interval. All right, so now one thing you can do, if we need to know which direction the particle is going. Now right now we really don't need to know the direction, but if you didn't know the direction of the particle, okay, we can always go some 0 and 3. We can put, okay, this is our critical number. You can put your critical number on a wiggle graph if you want to, and you can pick out a couple of test values and substitute those into your velocity function, and that'll tell you which direction that the particle is actually traveling, whether it's traveling to the left or to the right or up or down. But now to determine the total distance, I don't need to know which direction it's traveling. I just need to know how far it's gone. So as we set this up, now I do know that you change the direction to 2. So I want to set up 2 different integrals here. All right, so to work this problem, okay, we're going to do the integral from, so we're going to integrate from 0 to 2, so we get our total distance. So from 0 to 2, so 4t minus 8 dt. And I know it changed direction at 2. Now I don't know if it went to the left or to the right, but erase this, it did change direction at 2. Yeah, so from 0 to 2 plus the distance traveled from 2 to 3. So 4t minus 8 dt. I'm going to set this up as 2 separate integrals. We're going to find, now And also, as you look at this, now we're getting the absolute value. So the absolute value here plus the absolute value of that distance there. So no negative answer. So we're going to evaluate this integral, take the absolute value. So if it comes out negative, we've got to change the sign. And the absolute value of the integral from 2 to 3. Right? Now let's see, we just did the integral a second ago. That was, our integral was, 2t squared. 2t squared minus 8t from 0 to 2, absolute value here, okay, plus the absolute value of the integral, okay, 2t squared minus 8t from 2 to 3. Right, so the absolute value of each of those. Now, once again, I'm assuming that you know how to evaluate a definite integral. We found our antiderivative. Okay, substitute our upper bound minus our lower bound now. So let's see, the upper bound would be 2 times 2 squared minus 8 times 2, okay, minus 2 times 0 squared minus 8 times 0. Absolute value of this, okay, minus or plus the absolute value. Let's evaluate the other definite integral. Substitute the upper bound minus the lower bound. This would be 2 times 3 squared minus 8 times 3. Okay, minus, substitute 2 in for t now, gives us 2 times 2 squared minus 8 times 2 absolute value. All right, now I've already done the, I'm going to kind of skip the arithmetic here just to kind of move things along. And let's see, now this will give us 4, 8 minus 16. This is all 0 here. So 8 minus 16 will be negative 16, 8, so it'll be negative 6, absolute value of negative 6. Okay, plus, now as we evaluate the upper bound minus the lower bound in the second integral now, we end up here with the absolute value of negative 6 minus, now this here will simplify as negative 8. And we'll change this to plus a positive 8, and we end up here with 6 plus negative 8, negative 6 plus 8, which is 2. So it'll be 6, well, actually this will be negative 8, I'm sorry, this will be negative 8. So this is negative 8, which gives us 8 plus 2, or 10. Right, now this will be 10 feet, I believe. So the particle would have traveled 10 feet. Right, so this will be our total distance traveled of the particle. Okay, let's try another example. This time we'll do a quadratic example. So we get this erased. And let's take a look at our next problem now. So we're going to do 2 more. So we'll do and then we'll finish up with a trig problem. That'll be our last one. So we'll erase this. All right, so we'll erase this. Okay, so this time, let's see. This time for our second example, we pull this up. Okay, here we go. Now, once again, I'm going to be erasing this in just a moment, or taking this down in just a moment. So if you need to get a copy down, or you want to copy it down, you want to go ahead and get it down. Now, this says a particle has a velocity of v sub t equals t squared minus 7t plus 10 feet per second in the interval from 1 to 4. Find the displacement and the total distance. And once again, we're looking for the displacement and the total distance. So let's get the displacement first. This will be example number 2. And then let's see, our integral is t squared minus 7t plus 10. We're just looking for the displacement over the interval from 1 to 4. So our time interval, our lower bound is 1. Our upper bound is going to be 4. So we set our integral up. It'll be set up from 1 to 4 of t squared minus 7t plus 10. Okay, dt. Now, evaluating this definite integral will give us our displacement. Right? So that'd be our net change in position relative to the starting point of our particle. All right, now let's see. So as we set up, let's see what we get for our net change. Then let's find our antiderivative first. Now, our antiderivative will be let's see, t cubed. So it'll be t cubed. So it'll be 1/3 t cubed, and this will be minus 7 has t squared plus 10t from 1 to 4. All right. Now, let's substitute our upper bound minus our lower bound, right? So substituting the upper bound in first, this is going to give us 1/3 times 4 cubed minus 7/2 times 4 squared. So times 4 squared minus 10 times 4. Okay, minus, now substituting the lower bound in, gives us 1/3 times 1 cubed minus 7/2 times 1, okay, plus 10 times 1. All right. Okay, let me take our problem now. I think everybody got it. Right. Now, as we evaluate these, as we evaluate 4 cubed is 64, so you have 64 over 3 minus, this would be 8. 16, half of 8 is 2, half of 8, half of 16 would be 4, that would be 8 times 7 would be 56. This would be plus here, so this would be plus 40. Okay, minus, okay, here we have 1/3 minus 7/2 plus 10. All right, now to move things along, I did this earlier, this is 5.3333 minus, and then our our lower bound as we substitute in will be 6.8333, and this will simplify as negative 1.5 feet, okay, to the left. And so negative 1.5 feet to the left, that'll be, so this is our displacement of our particle right now. And like I said, we don't know which direction it's gone, we don't know if the particles change direction. Okay, we just know that it's negative 1.5 feet to the left of where we started. Right, so that's all we know there. Okay, let's do the second part of this problem. Now, the second part's a little bit more complex. So this time, for part 2, erase this. All right, now this time we're going to have to calculate the absolute value of t squared minus 7t plus 10, our velocity function from 1 to 4. Now, first thing I'll do, let's see if we have a direction change. So, do we have any direction change? All right, so any direction change. Now, that would be, this is when the velocity is equal to 0. So, setting this equal to 0 gives us t squared minus 7t plus 10 equals 0. Now, we've got to solve this little quadratic equation for t. I believe this one we can factor. So let's see, this would be equal to 0, so t and t, the signs are the same, negative and negative, this would be 5 and 2. Right. So we end up here with t equals 2, t equals 5. Right, so it's going to change direction 2 times. And also I noticed now the interval I believe was from 1 to 4, right? So from 1 to 4, so t equals 5 is outside our intervals. So we got to kind of watch out. We're just looking from 1 to 4. So within the interval from 1 to 4, it's going to change direction at 2. So it's going to change direction 1 time at 2. Now, I don't know if it changes direction from left to right or right to left. You know, so we don't need to know that. So we're taking the absolute value of from 0 from 1 to 2, and then from 2 to 4, and that'll tell us how far the particles change. So we're going to travel. So to get our distance, and once again, since they give us our distance. Right, so let's see what we get. So we erase this. So we set up our integral now. So this will be from 1 to 4 absolute value. All right. So we set up our integral, describing our interval. Now we're going to do 2 integrals. This will be from 1 to 2. T squared minus 7t plus 10 dt. Plus the integral from 2 to 4, t squared minus 7t plus 10 dt. So we're going to do the 2 separate integrals again. All right, so the upper bound minus the lower bound, and then we're going to take the absolute value of each of these. All right, so the absolute value of each of these. So, and let's see what we get. We erase this. We got our direction. We just changed the direction already. Okay, let's see. So let's see. Now we've already done the absolute. Let's see. We've already done the antiderivative, right? So this is 1/3. So the first integral here would be 1/3 t cubed minus 7/2 t squared plus 10t from 1 to 2, plus the integral 1/3 t cubed minus 7/2 t, plus 10t from 2 to 4. And we take the absolute value of each of those now. So let's evaluate the first integral now from 1 to 2. Substitute the upper bound minus the lower bound. This gives us 1/3 times 2 cubed minus 7/2 times 2 squared, okay, plus 10 times 2, okay, minus. Substituting 1 in for t now gives us 1/3 times 1 cubed minus 7/2 times 1 squared, plus 10 times 1, plus. And we'll take the absolute value of all of that. So we put our absolute value symbols on it. So we have to evaluate each of these, subtract, and then take the absolute value there. And let's see, I've already done the calculation on that. That would give us 8.6666. So 8.6666. We'll take out 4 decimal places. Now my final answer, I'm going to round off the 3 decimal places. The other here will give us 6.833, so 6.8333. Okay, plus. Now let's evaluate the integral from 2 to 4. Now the integral from 2 to 4, once again, this is 1/3 times 4 cubed minus 7/2 times 4 squared, plus 10 times 4. Okay, minus the integral, substituting 2 in for t. Gives us 1/3 times 2 cubed minus 7/2 times 2 squared, okay, plus 10 times 2. And once again, we'll take the absolute value of all of that, and which I've already done, and we get 5.333, okay, minus 8.6666, and the absolute value of those, right? This is the absolute value here. And then as we evaluate this, now we have the absolute value of 1.8333, okay, plus absolute value of negative 3.3333, and then adding the two together gives us 5.167 feet traveled. So that's how far the particle has traveled. That's how you need to do it. So once again, it's 2 separate integrals. Find if and where the particle has changed direction, and you have to set it up as 2 separate intervals. Now, if you do this on your graphing calculator, if you have one of the advanced graphing calculators, you can most of them will have an absolute value function on it. You can just as you type it into your function list, you can pull the absolute value function up, and within very, very quickly you can evaluate something like this on your graphing calculator. All right, now let's see, we want to do one more problem. All right, so one more. Let me get this erased now. All right, so let me get this erased. So one more problem. Let's try a trig problem. Let's try a trigonometry problem. So if I can get this erased, here we go. Go. Right, let's pull up problem number 3. Right, here we go. Right. Now, our last problem said the velocity function v sub t equals cosine t in feet per second is moving along a line. Right, so you have a particle, I assume, moving along a line. Find the displacement and the total distance traveled over the interval from 0 to 2 pi. So once again, same setup. And let's see our velocity function. So let's get the displacement first. Yeah. So let's do our displacement first. Now this would be the integral from. Here we'll be evaluating the integral from 0 to 2 pi of cosine t dt. Right, so this should give us our displacement. Now, this problem we'll do a little bit differently because I know what the graph of cosine looks like. And if you remember the graph of cosine, you have over particular intervals, you have the same area above the x-axis as you have below the x-axis. So some of these areas may cancel out. Now, if you look at the graph of cosine, so like so, and let's see, it's going to be pi, 2 pi here. 1, and negative 1. So looking at the graph of cosine, let's see, we've got, let's see what else. It's going to cross the x-axis here at pi over 2, and here at 3 pi over 2. So now what the graph looks like, let's make it a little bit easier to do this problem now. So the graph of cosine comes down like so, and down to here, and back up to here. So you get cosine looks like this. And from 0 to 2 pi, so just looking at the curve, we know about the graph, you can, as I look at this, I kind of imagine 4 equal areas. Let me bring this down right here. So you can imagine 4 equal areas. Area region 1, 2, 3, and 4. Okay, each of those are congruent areas. Right now, so if I'm looking at the total displacement, this is our velocity. Okay, this is over time. Okay, the particle has obviously traveled to the right from 0 to pi over 2. It changed direction at pi over 2 and now is moving to the left from pi over 2 to 3 pi over 2. And then at 3 pi over 2 it's changed directions again. And from 3 pi over 2 to 2 pi, the particle is moving back to the right. This particle is moving from the right to the left and then back to the right again. And it looks like it's gone equal distance. So just what I know about the graph on this one, I would say that the displacement here should be 0. Now, let's just check that to make sure. So what I'm going to do is this. I know these regions are all equal. So what I want to do, I want to integrate from 0 to pi over 2, and let's see what that distance is. How far has the particle traveled from 0 to pi over 2? All right, so I set my integral up of 0 to pi over 2 of cosine t dt. All right, and that'll give me the area of this first region here. So that'll give us that area there. Now the antiderivative of cosine is sine t from 0 to pi over 2. Substitute the upper bound minus the lower bound, so sine pi over 2 minus sine 0. Now sine pi over 2 is 1, so 1 minus 0 gives you 1. Right, so the area of region 1 is going to be 1 square unit. Right? So that would be, so our displacement from 0 to pi over 2 would be 1. So you think about this now. Okay, this region would be positive 1. This region here would be positive 1, negative 1, and then positive 1 again. So if we're looking for the displacement from 0 to pi over 2, each of those regions is 1. Okay, the displacement, so the displacement should be 1 plus negative 1 plus negative 1 plus 1. And so you add these up, it gives you 0. So the particle is basically right back where it started from. Right? And just by looking at the graph of cosine, you can see you have an equal area above the x-axis as you have below the x-axis. Those areas will cancel each other out if you're just looking for the displacement. Next, let's see what we get for the total distance now. So we did the displacement. Okay, what about the total distance? Now the displacement was 0. Now the total distance, okay, travel should be now, once again, a total distance. This would be the absolute value of the integral from 0 to 2 pi. So cosine t dt. That's the absolute value. So this would be 1 plus 1 plus 1 plus 1, or 4. Now, so the total distance traveled would be 4. The particles, that would be 4. In this case, would be 4 feet. So 4 feet traveled. So the particle would have traveled 4 feet. So it went to the right 1 foot, it went to the left 2 feet, and then to the right again 1 foot. So for a total distance of 4 feet. Right, so this particle has traveled 4 feet traveled a total of 4 feet. So just add them all up. This is the absolute value of the integral from 0 to 2 pi. And hopefully you've found our 3 examples here helpful as far as calculating motion along a line. We try to do somewhat of a variety of problems. We did the trig problem. We did a couple of polynomial problems. So hopefully you have some idea now about particle motion.